May it go smoothly for you.
We're good to kick off, Lisa.
Awesome. Thank you, Allie. And thank you, everybody, for joining us for today's conversations about carbon. I'm super excited to introduce Dr. Brian Hornbuckle and have a conversation with him around these topics. For those of you that don't know Brian, he is a professor in the Department of Agronomy here at Iowa State. He also has courtesy appointments in the Department of Geology and Atmospheric Sciences, and then also a courtesy appointment in electrical and computer engineering. His background is focus of study is atmospheric physics. I'm excited to talk with Brian because this is not a topic that I know in depth, and I expect to learn a lot from him as an expert in this field. A little bit more about Brian. He's a Iowa native from Shenandoah, Iowa. We both started here at Iowa State in 2003, so we're part of the same cohort of faculty members here. It's really been fun to watch his career here at Iowa State and some of the cool things that he's done. And in addition to the research realm, he's an expert teacher. And for those of you that don't know Brian and want to know more, he also has this wonderful biography on the web talking about previous positions that he's had and how some of those have inspired him to be where he is today because of the great experiences he had and some not so great, which are also defining in some ways and teach you that maybe things like biomedical engineering are not your cup of tea. And in Brian's case, it was really fun to read that biography of you, Brian. So thanks for putting that up there. I often tell my students that my path to get here, it may look linear to you, but it was really circuitous, and you really laid out some of the twists and turns that you've taken. And I think that's always so beneficial to students to see that, that their career might take some turns as well. So I guess, let's see, we're going to do this one a little bit differently. Brian wanted to do a brief presentation. He shared a presentation about the greenhouse effect at a climate science education conference not too long ago, and wanted to share that with us. Again, we want to get to some of the really key themes associated with atmospheric physics and how that relates to things like carbon dynamics and greenhouse gases. And so Brian's going to help us with some of those basics, and then we'll shift to the regular Q&A. I have some pre-prepared question and answer for Brian that I think can help us move the conversation in ways that our audience will find beneficial. And then of course, we'll open it up to the entire audience for questions as well. We want to make sure that we get your questions added. So if something comes up during Brian's presentation or during my Q&A, feel free, put that in the chat. We're going to prioritize the audience questions. So with that, I'll stop sharing my screen and then hand it over to you, Brian. Thank you again.
Okay, so again, just want to make sure that you can see what I'm sharing with you.
Looks great.
So like what Lisa said, this was a presentation I gave at, I think, the 2015 Climate Science Educators Forum down in Des Moines. I was with Ray Arrett, who was a faculty member here, and it's about teaching the greenhouse effect. And really the goal here of what I want to do is I want to make sure that as people, thinking about the carbon cycle and its effect on our climate, that we know what the greenhouse effect is, because some of the comments I've heard from people talking about the greenhouse effect aren't quite correct. And so here's one. I'm not a Catholic, I'm a Protestant, but I'm an admirer of Pope Francis and some of the progressive views that he's taken. And here in his encyclical about our common care for our common home, he talks about the greenhouse effect. And he says, it's true that there are other factors, yet a number of scientific studies indicate that most global warming in recent decades is due to the great concentration of greenhouse gases released mainly as a result of human activity. And then he says, concentrated in the atmosphere, these gases do not allow the warmth of the sun's rays reflected by the Earth to be dispersed in space. And I'm highlighting this last statement here because this is not physically consistent with our understanding of how the greenhouse effect works, what it is. And it's typical of language that's sometimes used to talk about the greenhouse effect. Now, whether or not we know exactly, we talk exactly about how it works, whether that's important. I guess one of my basic tenets is that I want to understand as much as I can about the basic physics of something that's happening so that I can make the best decisions about what to do about that. So that's what I'd like to share with you is how I think about the greenhouse effect in terms of the basic physics. So essentially, there are two sources of radiation that warm Earth's surface. And I want to highlight the radiation aspect here. That's what we need to be thinking about in terms of the greenhouse effect. One of those sources is the sun. It emits what we call shortwave radiation because it's really hot. And Earth's surface absorbs some of that radiation and warms. The greenhouse effect, I would describe it as the long wave radiation emitted by the atmosphere that warms Earth's surface. So again, distinction here, sun, we're getting what we call shortwave radiation, and the greenhouse effect is this long wave radiation coming from the atmosphere. So here's a diagram that I use in my weather and climate class that I teach. In fact, all these slides come from my weather and climate class. And really the only thing I want to point out here is that there are two sets of things going on. We've got what we call the shortwave energy budget here on the left that has to do with this shortwave radiation coming from the sun and what happens to it as it interacts with the Earth system. And then on the other side, we have other processes that move energy around within our Earth system. And one of those things here is labeled the greenhouse effect. And it's part of what we call the long wave energy budget of Earth's surface, of the Earth system. So here it is written out in words, kind of a short summary of what happens with the shortwave radiation coming from the sun as it interacts with the Earth system. So Earth's surface absorbs some shortwave radiation from the sun, and the surface warms up. And the atmosphere absorbs some shortwave radiation from the sun, and the atmosphere warms up a little bit. Earth's surface emits this long wave radiation, and the atmosphere absorbs nearly all of this long wave radiation emitted by Earth's surface, and the atmosphere warms up. But there are these other processes too that transfer the energy absorbed by Earth's surface to the atmosphere. And we call these things sensible and latent heat flux, are the two general terms here. And this sensible and latent heat flux associated with evaporation and transpiration of water. These fluxes from Earth's surface transfer energy to Earth's atmosphere, and the atmosphere warms up. And then here's the greenhouse effect. The atmosphere emits this long wave radiation. Earth's surface absorbs nearly all of this long wave radiation emitted by the atmosphere, and the Earth's surface warms. Okay, so that's a summary of what's happening here. Again, there are two flavors or types of radiation. Shortwave radiation is what we get from the sun. It's essentially the source of all energy here on Earth that drives our weather and climate. But within the Earth system, we have this long wave radiation that is what we should be thinking about in terms of the greenhouse effect. So there are two main physical laws here that are playing in this arena. Number one, we call the Stefan Boltzmann law. And essentially the stuff on Boltzmann law says that the hotter something is, the more radiation it emits. And this is hard for students to appreciate because everything is emitting radiation all the time, 24/7. And we can only see the radiation that's being emitted from the sun because that's the wavelengths our eyes can see. And that's because the sun is super hot, which leads me into the second law here called Wien's law, where Wien's law tells us about the type of the type of radiation that is emitted by objects. And because the sun is really hot, it emits shorter wavelengths of radiation most strongly. And that's why we call it shortwave radiation. While the Earth, which is much cooler, emits longer wavelengths of radiation, and that's why we call it long wave radiation, okay? So that's Wien's law that tells us about the type or color or flavor, however you want to think about it, of radiation that's emitted depending on the temperature of the object that's emitting that radiation. Earth only essentially emits long wave radiation because it's much cooler. So what happens to these two different types of radiation in the atmosphere? Well, it depends on wavelength. And that's a very key concept here. Radiation is characterized by its wavelength or equivalently frequency. You can think about it in terms of its color or type or flavor, however you want to think about it. But radiation behaves differently in Earth's atmosphere depending on its wavelength. So shortwave radiation, what I have here is the percent of radiation absorbed by the atmosphere from 0 to 100 versus the wavelength of radiation in micrometers. And you can see in this region that we call shortwave radiation, the atmosphere is fairly transparent. Yes, there are some wavelengths that are absorbed by the atmosphere. So some shortwave radiation warms the atmosphere, but a lot of it gets through, which is in contrast to our long wave radiation over here, where the atmosphere is mostly opaque. Now, there isn't what we call the atmospheric window here, where some long wave radiation gets through the atmosphere. But in general, the long wave radiation is absorbed by the atmosphere because of these greenhouse gases that are in the atmosphere, particularly water vapor, the number one greenhouse gas, carbon dioxide, so forth and so on. Now, here's another important point about the greenhouse effect is that if we didn't have this long wave radiation coming from the atmosphere, warming Earth's surface, Earth would be really cold. So Earth's surface is much warmer because of this greenhouse effect, because we're getting radiation both from the sun and from the atmosphere. And so one of the things that I try to highlight in my weather and climate class is that there are good and bad things about the greenhouse effect. One really good thing is that it's essential for life here on Earth. It would be way too cold if we didn't have the greenhouse effect. We wouldn't be able to grow anything. And of course, that means we wouldn't be able to live here. However, just like eating candy, sometimes too much of a good thing is bad, right? So as we add greenhouse gases to the atmosphere, we will increase this long wave radiation that's being emitted by the atmosphere that's warming Earth's surface, and that's going to cause climate change. So there are two things that I do in 206, my weather and climate class, to help students think more about the greenhouse effect. One, I hand out infrared thermometers so they can start thinking about this invisible radiation, long wave radiation that's all around us. We can't see it, but it's there. And then the other thing we do is we sing a parody to a Journey song here. We sing the radiators in the sky keep on burning. It's not at all like a greenhouse. So that's something that I do to help people think about the greenhouse effect in a different way. So here's a question that I ask on the first exam of every weather and climate class. I don't tell my students this, but I ask them to tell me about the greenhouse effect and whether it's good or bad, and to justify that response. And here's the key, what I'm looking for out of 5 points. I want them to tell me that the atmosphere emits long wave radiation, which warms the surface. That's the greenhouse effect. And they can argue whether it's good or bad. I don't care which, because it's both. And then I want them to write in complete sentences. And here's a sample from 1 year about what I get back from students. Now, a lot of them are able to tell me that the greenhouse effect is good and bad, but unfortunately, not a lot get to the full understanding, because we've got these misconceptions about the greenhouse effect. And here's some of them that are caused by the name. So I don't like, maybe we could call it something else maybe, because it's really not what a greenhouse does, right? So what a greenhouse does is it traps these other fluxes, specifically sensible and latent heat flux, from transferring energy from Earth's surface to the atmosphere. And that's why a greenhouse is warm. It's not anything to do with long wave radiation. So it's really a misnomer, the greenhouse effect. Here's some things from a paper by Julie LeBarkin. I think she's from Michigan State. She surveyed students and had them draw pictures about what they thought the greenhouse effect was. And so here's the key that she used to illustrate some of the things that they drew. And one thing they drew had to do with plants. Well, plants don't cause the greenhouse effect. There's just, there's really no relationship there at all. So that's one misconception. Another misconception that we often hear is that the greenhouse effect traps energy from the sun like a blanket. Now, this is an okay conceptual model for, your average person, but as scientists, we need to get past that, because it's not about shortwave radiation, it's about long wave radiation. There's no reflection that's happening, and there's no insulation here that's causing the greenhouse effect. In fact, long wave radiation is not reflected by Earth's surface or the atmosphere at all. The atmosphere is a very good absorber of radiation, and so is the Earth's surface. Here's another misconception. Doesn't have anything to do with the ozone hole. So some of the students that she surveyed would draw in the ozone hole. Now, this gets a little confusing because ozone is a greenhouse gas, but the fact that we have less ozone at the South Pole and now also at the North Pole at different times of the year doesn't have anything to do with the greenhouse effect, this long wave radiation that's emitted by the atmosphere. And then one of my pet peeves here is when people say that the atmosphere re-radiates long wave energy. And this is a pet peeve of mine, because the only reason why the atmosphere emits radiation is because of the Stefan Boltzmann law that says everything with a temperature above absolute zero emits radiation. And this energy that the atmosphere has doesn't just come from long wave radiation from Earth's surface, it also comes from these other processes. It gets a little bit of energy from shortwave radiation directly from the sun. It gets some from latent heat flux from Earth's surface, and it gets some from sensible heat flux from Earth's surface. So about 2/3 of the energy that is warming the atmosphere comes from this long wave radiation emitted by Earth's surface, but 1/3 does not. So why do we have the greenhouse effect? Because the atmosphere is warm, and everything that is warm emits radiation. So how would I change this section from Pope Francis's letter? Well, instead of saying concentrated in the atmosphere, these gases do not allow the warmth of the sun's rays reflected by the earth to be dispersed in space. You know, first of all, the problem here is it's not about shortwave radiation coming from the sun, and it's not about any kind of reflection that's happening. So I would change it to this way. I would say, concentrated in the atmosphere, these gases do not allow the warmth of the long wave radiation emitted by the earth to be dispersed in space. So I don't know if you noticed at the beginning, I had a little picture of a radiator on the first slide, but that was a set here to make you, maybe hopefully you started thinking about a radiator. And really, I think that's the best way to describe the greenhouse effect, as a radiator in the sky, because there are two sources that warm Earth's surface. Number one, the sun, but the other is the atmosphere. And it's this long wave radiation emitted by the atmosphere that is what we call the greenhouse effect. And maybe it would be better to call it the atmospheric effect, or the atmospheric radiator effect, which is more physically accurate and can help us get to more sophisticated models of our understanding of the greenhouse effect. But I doubt that we're going to start calling it that, right? So, and then the other thing that I would like to emphasize too is that, you know, without the greenhouse effect, we couldn't live here on Earth. It's essential to life on Earth. The problem is that too much of a good thing can be bad. So that's where I'll stop right now and take questions.
Awesome. Thanks, Ryan. And I think I'm going to have Journey, that Journey song parody going in my head for at least the rest of the day, maybe the rest of the week. So thank you for that. And also the candy analogy. That really works for me. So thank you. That was great. I want to start out with some other basics in terms of some of the questions here. So when I'm reading reports and such, I'm oftentimes seeing lots of different terminology, some of which you already covered in here. But there, in addition to sort of greenhouse gases, there's another couple of terms that you oftentimes see in reports. I want to make sure that's clear to our audience. So greenhouse gases, heat trapping gases, trace gases, to what extent are they synonymous versus where are we, where are we not, apples and oranges on those terms?
Right, so greenhouse gases would be the gases in our atmosphere that have a molecular structure in a way that allows them to absorb photons of radiation in the wavelengths of infrared and what we call long wave radiation. And so these would be things like water, for example, that has different energy levels that a water molecule can transition to. So the way I imagine it is, here comes a photon in of light, little bullet of light, and it has, let's say, wavelength in the long wave region. The water molecule can catch that photon and move from one energy level to a higher energy level, and that's what absorption is. So now its energy state is higher, and then later the water molecule can move back down to a lower energy level, and in that process emit a photon of radiation that would be also in that long wave region. So there are lots of molecules that can do that. Carbon dioxide can do that. Water vapor, ozone, methane, nitrous oxide, those are all what we call the greenhouse gases, because they are really good absorbers of long wave radiation and emitters. And so calling them heat trapping gases, again, is a little not quite physically consistent with what the greenhouse effect is, because it's all about radiation. It's not about like a blanket or something like that. trace gases would be just the gases that are in small amounts in our atmosphere. Number one is nitrogen, then oxygen. Number three, trivia question, is argon. But then we have lots of other gases that are important, but just found in very small amounts in the atmosphere, and that would be trace gases. And I think that's the three that you talked about.
Yep, great. Thanks for clarifying those terms for us. So you mentioned three big ones, right? Carbon dioxide, methane, nitrous oxide. One of the things I also want to make sure to clarify is the longevity of those molecules in the atmosphere. They have different longevities. And so why the different longevities? Why are we concerned about those three compared to, say, other atmospheric gases like the you mentioned water vapor, or also ozone, right? So why are we concerned about those three, their longevity? And then how do scientists go about measuring the longevity of these things in the atmosphere?
Yeah, okay, so first on longevity, the technical term we use is something called residence time. And so here's some residence times of common gases. So nitrogen gas, millions of years, all the way down to water vapor, tens of days. So here's kind of a fun story about water vapor, is that when I was in graduate school, a official from Ford Motor Company came and was talking about climate change, and he was bragging about how Ford has reduced its water vapor emissions. And water vapor is the #1 greenhouse gas. And that is true. Water vapor is the #1 greenhouse gas, but we're not worried about it because it rains out of our atmosphere so quickly. It doesn't hang around at all. Whereas things like carbon dioxide hang around for hundreds of years. And the reason why carbon dioxide does that is best illustrated with the second slide here, is that carbon dioxide is part of the natural flux of energy and water and mass between Earth's atmosphere and surface. And if we just thought about the fluxes between the land and the atmosphere and the ocean and the atmosphere in terms of carbon dioxide, maybe residence time would be on the order of years, something like that. But the problem is that we had this other flux of carbon dioxide that doesn't have a corresponding sink, and that's fossil fuels. And so this turns the residence time into hundreds of years. And so what does this residence time depend on? Well, mathematically, the residence time is storage in the atmosphere divided by flux. So if you have lots of storage in the atmosphere, like for nitrogen gas, it has a huge residence time because there's a ton of it in the atmosphere. But then in other cases, the flux becomes important, right? If you have a large flux, then you can have a short residence time. So all these different gases have different ways that they move between Earth's surface and the atmosphere can hold different amounts. And those are the two things that determine the residence time.
Great. And so how do scientists go about measuring those things?
Not too sure, actually. I'm not a person that does that,
Okay.
But there are ways to measure carbon flux for sure, right? So right now I'm working with Andy Van Lukey, and we're measuring carbon flux also with sensible latent heat flux from a cornfield out at his research site west of town. So that would be one way to measure flux. Modeling is another way to measure flux in terms of capacity of the atmosphere. I guess it essentially would be a modeling exercise to predict. We're not going to measure, right, the atmosphere, but we're going to infer things from other things that we can know.
Great. Awesome. Thanks for that. That's helpful. Just a reminder to folks in the audience, put your questions in the chat, and I'll make sure that we ask Brian to answer those. I do have another question for you. Earlier this month, there was a lot of news around methane. The United Nations released a report calling for urgent action focused on methane in the atmosphere. Can you tell us a little bit about, why methane rather than carbon dioxide and nitrous oxide? And then, what role does being in Iowa, an agricultural state, what does that mean for us?
Right. So methane is the number 2 anthropogenic greenhouse gas. And I looked up this morning in the IPCC's most recent report, and the radiative forcing, in other words, the amount of warming that we can attribute right now to methane, is more than half than what we attribute to carbon dioxide. So carbon dioxide is definitely number 1, but methane is right up there. It's number 2. The other thing that's interesting about methane is that its residence time is much shorter than carbon dioxide. And I don't know if you saw on my slides, I had tens of years, but I'm going to revise that now because when I read the UN report, and it's more like a decade, about 1/10 of a year. So about 10 years. So that means that once it gets into the atmosphere, it's going to come out much more quickly, which also means that if we can make changes in the amount of anthropogenic methane emissions, then we're going to see results a lot sooner. Now, this should not take away our focus necessarily on reducing carbon dioxide in the atmosphere, but methane is an opportunity to make some big gains in a much shorter time period.
Great. Thanks for clarifying that. We have a question here from Robert Brown. What is your opinion of geoengineering the planet to mitigate climate change? Maybe start with
right.
defining geoengineering.
Right, so geoengineering, the idea is let's make some kind of physical modification, and it's really a large scale physical modification to the properties of our atmosphere or surface to reduce warming. So one example would be, let's seed clouds so that we increase the amount of clouds, and clouds are really good at scattering shortwave radiation back out to space. So it would increase what we call the albedo of the Earth system, which would lead to cooling. So what's my opinion of that? This was a very controversial idea a few decades ago, but there was a National Academy report more recently that said, we should put all options on the table because the consequences of increased climate change are pretty dire. So my opinion, I guess, would be that it could work and we should think about it, but it would be a big step because, there's always so many things that we learn when we try new things, and there could be some unintended consequences that could be disastrous if we do it on a global scale. So I think it's much wiser to try to do these other things that are essentially all positive, as opposed to trying something that could have some real negative aspects to it.
Yep. Great points. So we have another question here from Jim Dyer. It says, the question is, what is the half-life of methane?
So I'm not sure.
Why is that important, the half-life?
Yeah, well, I'm not sure. Half-life has to do with the fact that the residence times are likely, if you plotted abundance of a gas in the atmosphere versus time, the curve would likely be exponential. It's not linear. So a lot of it would go away quickly, but then some of it would hang around for much longer. I'm not exactly sure how residence time is defined in the scientific literature because it's not my area of expertise. So I can't answer what the half-life of methane would be.
Okay, great. Let's talk a little bit more about methane and the role that Iowa might play in terms of curbing methane emissions. Realize that your focus is on the atmosphere, but can you talk a little bit more about the sources of methane to the atmosphere and agriculture's role?
Right. Yeah. So what I've learned from the UN report that I read this morning is that there are basically three sources of methane, anthropogenic methane emissions. And I'm blanking on one of them right now, but one of them is definitely fossil fuel production. So my understanding is essentially that some of the, I know what the other one is. Some of the methane is generated in that process, and it's just kind of leaking out of the system. And if we could do a better job of tightening up that system, we could reduce methane emissions and make it more save money, basically. Another one is when decomposition from landfills is another source of methane. And so again, capturing those gases would make a difference if we can do that in a better way than we are now. And then the last one would be agriculture, with the biggest one being enteric fermentation from animals. And so the solution there, I know that there's some animal scientists that are thinking about how might we breed new strain or new genotypes, essentially of phenotypes of cattle that would be able to digest food in ways that would not release as much methane.
Great. And then the other source associated with agriculture is going to be emissions through manure. So there's the front end of the animal, and then there's also at least with cattle, right? And then there's the back end of the animal too that we have to be attentive to. And of course, same with our own waste as well. So you mentioned that with sort of waste treatment and such.
Yes.
Great. Good. I guess one other question that I have is, as we talk about mitigating climate change and we talk about, carbon drawdown, you mentioned, geoengineering, some concerns about that because it would be a big step with lots of unknowns and potential unintended consequences. From your standpoint, looking at the science, what would be some of the solutions that you would like to promote, or your favorite solution, I guess, if you were to pick one or two?
Yeah. Well, I can comment on a few. I don't have a favorite one, but some interesting things have for me in some of these things. So we talk about carbon sequestration in the soil as a way that agriculture could play here. So my main question there is, how are we going to quantify how much carbon is being sequestered? My research has to do with careful validation of remote sensing measurements, and we always think about whether or not we're sampling enough, and are we scaling up our measurements made at one spot to represent a bigger spot in the right way. And so again, I think there's a challenge there to really understand how much carbon is being sequestered and how to measure that. The other comment I would make is that in terms of reducing our reliance on fossil fuels, I have some relatives now that are not really thinking about the environmental aspect of all this, but they're really motivated by the economic aspect of this. And one of my relatives is the first to put solar panels on their house. And it's totally an economic decision rather than an environmental decision. And we're all driven in some way by economics, but that is just highlighting to me how important it is to show the general public that there's what the benefits are to their personal lives. It's hard to think about kind of these longer term benefits for a lot of people, but the shorter term benefits are there, and we need to make sure that we're emphasizing those.
Great. Yep. Thanks for bringing up those human dimensions. They're so crucial in all of this. I want to pivot back to something that you said about the monitoring component and how important that is as well. So I've been in some discussions about developing carbon markets, and one of the things that people that are active in that space say is that the more we can do to reduce the cost of that monitoring and verification, right, the more opportunity there probably is that carbon markets can actually return more of the dollar, right, to farmers. And so, based on what you know of the science, what are some of those key question areas in the monitoring and verification area, and how can innovation in that space help reduce the cost of that piece of the puzzle so that we can preserve more of that dollar for farmers?
Right, so I haven't worked in that area, but I can give an analogy in the area that I do work. So my research has to do with using satellites to tell us about the water in the soil and in plants. And the challenge, again, is that these satellites, the finest detail that they can see is the size of Story County, all right? So it's big. So the challenge is for us as remote sensing scientists is how do we prove or how do we validate that these soil moisture measurements that we're getting from satellites are really correct? And the best way that we've come up with right now is to put out sensors, soil moisture sensors in the soil, and put out enough of them so that we think that we're characterizing adequately how much soil moisture varies in space and time within an area size of Story County. And right now, our community believes that if we have about 20 of these soil moisture stations spread out in Iowa County, essentially, that is the truth in terms of soil moisture. But when you think about it, soil moisture can vary from here to here. Mm-hmm. And it's kind of crazy maybe to think that I can put an instrument in the ground that's measuring a volume this big and somehow compare that to what a satellite is measuring over the whole county, right? Mm-hmm. So to me, that's going to be the challenge, is finding out developing the technology to make measurements, and then figuring out how to scale them up to a field, up to a township, up to a county, up to a state. It's something, again, we struggle with in my area of remote sensing. I think remote sensing is the way to do this. Mm-hmm. But the other thing about remote sensing is that it's an indirect measurement. It's measuring radiation, and that's not necessarily what you want, right? You want something else like soil moisture or carbon. And so there's another challenge there, is to make that connection, which is also influenced by other things.
Great. Thanks for clarifying that for us, Brian. And I totally agree that there's a really awesome opportunity for science in terms of environmental monitoring, and especially figuring out how to scale better. We can't measure every single point on the Earth's surface, and so we have to be able to do a better job of taking the measurements in the right place and being able to scale it up into a meaningful way that can help decision makers in terms of the decisions that they have to make. Thank you all. I'm going to pivot. Thank you, Brian, for sharing your expertise with us, for helping to dispel that myth associated, that's widespread myth in terms of how the greenhouse effect actually works. Really appreciate it. I learned a lot. I'm sure our audience did as well. Thank you so much. I'm going to share my screen again for some closeout slides here as we wrap up, and just let you know that next in 2 weeks we'll have another conversation about carbon with Jill Yukin. Jill is retired now from the Iowa State Bioeconomy Institute, but in addition to that role, she wore many hats. She is, along with her husband and daughter and son-in-law, operate Yukin Farms in Southwest Iowa. She's also a board member of the Southwest Iowa Renewable Energy Corporation, and is willing to share her expertise as a farmer, as a board member in that renewable energy venture. And then also just everything that she's known from working here at Iowa State, lots of scientists and industry in her role at the Bioeconomy Institute. The title of her talk will be Farmers and Ethanol Producers' Perspective on Carbon Sequestration. So she has a very, view from the ground perspective and a farmer perspective that I think it's important to get into the conversation. Also, just to kind of give you a heads up, we're going to take a break in July and August from conversations about carbon. Many of us are going on vacation, and Allie is busy scheduling some other events during that period. So we're going to take a little break. But we're in the process of putting together a robust schedule again for when the semester starts beginning on September 1st. If you have thoughts about people that you would like to hear from in this series, really would encourage you to submit your ideas here. Here's a QR code or a tiny URL that will get you to a Smartsheet form where you can enter who you would like to hear from. We've already heard from several people that have been entered by the audience members in this forum, and Brian Hornbuckle being one of them. So thank you again, Brian, for helping increase our knowledge and understanding with regards to the greenhouse effect and greenhouse gases and climate change and all of these things. We really appreciate you sharing your time and expertise. And thank you to our audience for listening and questions.